Okay, just let me know if you can hear me and see my slides.
Yes, we can hear and see your slides.
Okay, okay. Again, good morning, everybody, and thank you for the opportunity to present my results here in this conference. I'm going to present the results about the pulverization methods and their influence on the microstructure of carbon aerogels. And first of all, for those of you who are not familiar with aerogels, aerogels are solid materials with a highly porous structure. And the pore structure is an open structure so that the pores are connected between each other. And carbon aerogel are mostly produced from organic aerogels, and they found a very broad application in the as an electrode material, for example, for energy storage devices, for batteries or supercaps, also as additive for foundry applications, as a catalyst support or hydrogen storage and adsorption applications, and also as a medical agent and drug delivery system. You can see on the right side SEM image from carbon aerogel. So it has, you can see here secondary particle which consists of very, very small primary particles. And due to this architecture, the porosity is very high of carbon aerogel, up to 99%. So in our study, we investigated how the pulverization methods can influence the changes in this microstructure of carbon aerogels. And for that, we investigated three methods. The first method is the grinding. So we just use the grinding paper and grind our samples and collect the powder. And as you can imagine, this method is very fast and cheap. And also the energy impact is very low. We apply very low forces to pulverize the samples. The disadvantage of this method is the low reproducibility. So it means if I grind my samples or another person, then we will apply different forces and also different speed of the grinding. So this is not good for the statistical investigations. The second method is the shaker mill. Here you can see the how it looks like. So here we have our sample and steel bar, and by frequent percussions, the steel bar moves from one side to the other side with a certain frequency, and the whole of this machine is inside of a liquid nitrogen bath, so that here with this method we can embrittle the samples. So it's very important, for example, for very soft materials such as rubber or cellulose materials, bio-based polymers, and so on. Here we have for sure a higher energy impact compared to grinding. And the third method, which was already presented by a previous speaker, is the planetary ball mill. Is the maybe most used method of pulverization of samples. Here we have very different forces. And so the energy impact is the highest in this method. So these three methods we compared with each other. And now I'm going to present the samples we prepared. So back to the carbon aerogels. They could be prepared by different precursors. So as I have mentioned, first of all, we need to prepare an organic aerogel, and it can be then carbonized to carbon aerogel. As a precursor, you can use very different chemicals. So, for example, resorcinol and formaldehyde, or resorcinol and melamine and formaldehyde. You can also use some bio-based polymers and so on. And after mixing the chemicals, we induce the salt gel process. And once the gel is ready, it can be washed and dry supercritically in supercritical CO2 in an autoclave, or it can be just dried in an oven at ambient pressure. And then after drying, we will get an aerogel. So it means the pores of gel are filled with air. And then after carbonization, we get the carbon aerogel. And typically carbon aerogels are in the like monoliths. And for applications, they need to be pulverized. So for example, if you use carbon aerogel as an electrode material for battery, for example, then it needs to be milled to a certain particle size, and then it can be used in a slurry for a battery. The synthesis parameter influence crucial the final structure of aerogel. So in the synthesis we have different parameters which we can adjust to get the final structure which we like to have. For example, certain particle size or pore size, or the pore size distribution can be adjusted, the connectivity between the particles, and the microstructure influences the properties of carbon aerogels. So for this study, we prepared three different carbon aerogels. The PCI is a carbon aerogels which is ductile. Ductile means you can compress the sample and you change the size of the sample, so you can see the plastical deformation in the sample before it breaks. And then the SCA is a stiff carbon aerogel, and the FCA is a flexible carbon aerogel. So it means it is a soft material which you can like deform like a rubber. So here you can see the synthesis parameter. So we use a different amount of resorcinol and formaldehyde. The water amount was different, and also the pH of the initial solution, and the drying conditions were different. So we dried some of aerogel in supercritical CO2, and the SCA was dried in the ambient pressure. And then we carbonized them to carbon aerogels. So these three carbon aerogels with very different mechanical properties, we then milled with three different milling techniques, and then look to the properties. And first I'm going to show you the SEM images of PCA, so the ductile aerogel. You can see here the monolith. If we grind it with the sandpaper, then we can see very different particle sizes, so a very inhomogeneous powder. In the shaker cryomill, we can see also different particle size and also different granule size. In the ball mill, the particle size became homogeneous, and after repeated ball milling, we see that the particle size is quite similar. So we could get a homogeneous powder of this aerogel. The stiff carbon aerogel, here we see the structure is quite different compared to the PCA. So the particles are quite large. And after grinding with the sandpaper, we see that we didn't change the structure. So we just can see some broken particles or the connection between the particles. And then in the shaker cryomill, we see also inhomogeneous particle sizes. And finally, in a ball mill and a repeated ball milling, we see that we could break the particles to smaller particles, but still the homogeneity is not that high. So if we need for our application homogeneous particle size distribution, we need to repeat this ball milling to get it homogeneous. Then have a look to the flexible one. The flexible carbon aerogel has a very very small particles, and if we grind it with the sandpaper, then we see that the structure is not changed. We cannot see some smaller particles. After shaker cryomilling, we see that we just somehow compressed the produced granules to very compact particles. So the structure is completely changed. Also, the ball milling did not lead to some homogeneous powders. It is the particles are very, very different in the particle size, so that here we need maybe another method to prepare homogeneous powder. After we looked at the structure, we performed some nitrogen sorption measurements, and here you can see the results. So we measured the surface area with nitrogen sorption technique, and also the skeletal density. The skeletal density means that it is the density of the solid network, so without the pore volume. The skeletal density was measured by helium pycnometry, and here we see that all of the samples, so here the PCA, the SCA, and the flexible carbon aerogel, they have all similar skeletal density, which was expected because we do not change the chemical structure of the material. Then just have a look to the surface area. It is in square meter per gram. And here we have, again, our 3 samples with different techniques. And we see that, so the black columns are for the monoliths, so the initial structure. And then the white is for sandpaper. Shaker cryomill is the gray one, and then dark gray and another gray color for planetary ball mill and the repeated ball milling. And we see here very clearly that after grinding, we could somehow increase the surface area, which was not expected in our measurements. And at that stage, we couldn't explain why the surface area increased. If you see to the stiff carbon aerogel, here we cannot see some changes. So the network of stiff carbon aerogel is so stable that we couldn't see here some large differences. If we look to the flexible carbon aerogel, here we see the most changes. So the flexible aerogel is a very, very soft aerogel, so that even after very low energy impact grinding, we could change the structure, which was not expected. And also the other techniques, the shaker cryomilling and the ball milling, here we also could increase the surface area of the sample. Then if we look to the pore sizes, so the pore sizes, micropore volume and mesopore volume. So the micropores are pores below 2 nanometers, and the mesopores are pores between 2 nanometers and 50 nanometers. So we calculated by DFT model the micropore volume, and can see here that PCA has the lowest micropore volume, and the stiff carbon aerogel and the flexible one, they have a quite high micropore volume. And here we see again that in the ductile carbon aerogels, we could increase the micropore volume. The stiff carbon aerogels show very, very small differences in the structure. And again, the flexible one shows very high differences in the micropore volume. When we look to the mesopores, so the pores between 2 and 50 nanometers, we see that very high increase in mesopore volume was observed for the PCA, so it is a mesoporous carbon aerogel. And even in a stiff carbon aerogel, we can see very slight differences. And also for the flexible one, here we could again increase the pore volume. In the next step, to explain these results, we performed also other measurements. Here you can see again the nitrogen absorption results. These are the isotherms at 77 key, where we can see that the shape of the isotherm and also the shape of the hysteresis was changed. For further investigations, we performed wax measurements. Here we have our 3 samples, the PCA, the SCA, and the FCA. And here, if you look to the X-ray scattering curves, we cannot see some differences. So all of the aerogels are turbostratic in the structure, which is typical for amorphous carbon. And then by using of algorithm by Ruland and Smarsley, we could calculate from the wax curves, we can calculate the parameters of the microstructure. So it was done in the University of Gießen, these measurements, and by using of this algorithm, you can calculate the graphene stack size, the distance between the graphene layers, and also the deviation of those. And here, it was surprisingly for us, if you look to these results, so LA is the average graphene layer size, like is shown here, and we can see that for all of 3 carbon aerogels, we see that this graphene layer size was decreased. So it means the graphene layer sizes, or this graphene islands, they were decreased in the size. And maybe, as you know, the surface area depends on the particle size, and the smaller the particles, the higher the surface area. So, and it means if we decrease the size of the graphene layer, in that case, we increase the surface area. And that explains the previous results I have shown. Also, if we look to the average stack size, so the like a number of graphene layers, we can also see that we decreases this stack size, which was not expected, because even with the sandpaper, we could already change the structure. Then if we look to the standard deviation and also to the average interlayer spacing, we can see that it was quite constant. So if you see here, we have 3.6 angstrom to 3.7. So it is quite constant, and also the standard deviation is quite constant. There are some very, very low differences in between, which can also affect the pore size, especially the micropore size, which can be measured with nitrogen sorption. And so I come to conclusion. So the carbon aerogels can be used for very different applications. And in the most of the applications, they need to be pulverized. And we just have to have or we just shall look to the structure after pulverization, and the pulverization methods can change the structure, but the changes are also dependent on the mechanical properties of carbon aerogels. Yeah, and on that I will say thank you for your attention, and also thank you for our department, for aerogel research group, and I'm happy to answer your questions.
Thank you so much, Professor. That was a wonderful presentation. If anyone have any comments or questions, you can please ask Professor Marina.
Can I ask a question? I'm the next speaker, Wunderlich. So you showed in one slide, my question is, how strong is the bonding between the carbon atoms in the aerogel? In one slide, you had a picture which looked like crystalline materials, and in the other picture, more like polymers, van der Waals bonding. So how strong is the bonding?
I didn't really get the question. How strong is the bonding between carbon atoms, or?
Yes.
So this is a very is an amorphous carbon with sp2 sp3 hybridization. So after carbonization, we have a very low amount of hydrogen and oxygen bonded to the carbon, but this amount is really very, very low, maybe 2 or 1 between 1 and 2%. And yes, I don't know if I answered your question.
Okay. Is it more polymer-like or more covalent bonding? As you said, your material is ductile, very much ductile. So, so obviously not so strong bonding between the atoms.
Okay. Yes. So maybe I will go back to the SEM pictures and can show you, for example, here. So the mechanical properties depends very strong on the connectivity of the particles. Here it is like a it is a covalent bonding. They are covalent bonded with each other. But if you see to this next between the particles, you see here maybe. So if the necks are like a broad necks, then the stability is very high. And if you have like a points connected particles like pearls on string, then the mechanical properties are very poor.
Okay, thank you.
You're welcome.